Okay, so last time I went over 3.7. We don't have to do 3.8. Next section is 3.9, which is about related rates. So, for example, when you inflate a balloon, you can see that couple of variables. As the balloon gets inflated, its radius gets bigger, so does its volume. So if we know the rate at which the radius is increasing, how do we find the rate at which the volume is increasing, for instance? And for another example, there's a lot of examples, but this is another, pouring water in a cone. Pouring water into a cone. Again, if you're looking at a cone vertex down and you pour water in there, then the level of water is rising, as well as the radius of the circular surface of the water, as well as the volume is getting bigger. Okay, so there's a lot of examples, a lot of applications about related rates. We will discuss the steps for related rates, the strategy, and then we'll see a lot of examples. Strategy for solving a related rates problem. I'm gonna write down the steps there in your notes, but you need to draw a picture and name the variables and constants. We will use t for time, assume all variables are differentiable functions of time. So that's given. We don't have to worry about differentiability, but we want to label everything. Then we want to write the numbers that correspond to each variable. And then what are we asked to find? Okay, usually I want a rate. A rate is always a change of variable relative to time. dH by dt, dr by dt, dv by dt. That's what we're usually asked to find. And the most important step is to get an equation that relates all the variables. Sometimes an equation could be the Pythagorean theorem, one of the trig identities, volume of a cone, volume of a box. I don't know which, I just listed a few of them for you. Write an equation. Sometimes you have to combine two equations. Differentiate using implicit differentiation for the most part. It could be implicit, explicit, and we will need chain rule for the most part. Then you plug in the known values to find the unknown values. So these are general steps. We might have to use some of them at some time or all of them at other time. Now, what I want to start with is the very classic related rates problem, which is a ladder problem. And it's on page 50 in your notes. Example 1. It says, again, it should be in front of you when we're doing this. Page 50 in the notes. A 5 feet ladder leaning against a wall slips in such a way that its base is moving away from the wall at a rate of feet per second. At the instant when the base is 4 feet away from the wall, how fast is the top of the ladder moving down the wall at that instant? So what I'm going to do, just like the step says, draw a picture and name the variables and constants. So the picture, we have a ladder leaning against a wall. Of course, the wall is vertical. This is the wall. So there's a horizontal distance between, and the ladder is going down. It slips down. So this is going to be moving out, right? Because the ladder will slip. And it makes a 90 degrees angle. So we get the right angle. So it could be the Pythagorean theorem. We don't know. So the ladder is 5 feet. That's a constant. It's not going to change. This is changing and that's changing. So I'll just label them as y as an x, just like the notes, so you don't get confused. How fast is the top? Okay. Slips in such a way that its base is moving away. So the base of the ladder is moving away from the wall at a rate. So that's the derivative right there. At the rate of 2 feet per second. So x is changing at the rate. So dx by dt is positive. Why positive? 2 feet per second, because that distance is getting bigger. Okay, because the ladder, the base of the ladder is moving away, so that's bigger. So that's why it's positive. If it was getting smaller, that would have been negative. Okay. So this instantaneous rate of change, when was that at? Exactly when x was 4 feet. Right at that instant, they measured the speed or the rate of change, instantaneous rate of change was 2 feet per second. right when x equals 4 feet. How fast is the top of the ladder moving down? So how fast is the top of the ladder moving down? So we're talking about the rate of y, and we expect that to be negative because the y value is shrinking as the ladder is moving down at that instant when x equals 4 feet, right when x equals 4 feet. Okay, so we got the picture. We use t for time, assume the variable. Okay, write down numerical information. We did. Write down what you're asked to find. We did. dy by dt. Write an equation so that relates the variable. The common sense equation in this case is the Pythagorean theorem, which is x squared plus y squared equals 5 squared, which is 25. And then differentiate both sides with respect to t, again using implicit differentiation. Just be careful this time though. We're not doing d by dx. If we were doing d by dx of x squared, we would get 2x dx by dx, which is just 2x. But if we're doing d by dt of x squared, which we are, it would be 2x dx by dt. Don't forget that, okay? So x is not the independent variable anymore. T is the independent variable. T is the independent variable. So that would be 2x dx by dt. Same with the y. 2y dy by dt, and derivative of any constant, no matter what the independent variable is, it's going to be 0. Now we're going to plug in the values. 2 is 2, right? At when x is 4, we'll put that. Dx by dt is 2. We don't have y. Dy by dt is the unknown. So we still have to find y. But which y are we finding? Right at the instant. This y that we need right at the instant when x is 4, because that's what we're finding. So if we do the Pythagorean theorem, x squared plus y squared equals 5 squared. 16 plus y squared equals 25. Y squared is 9. So right when x is 4, y is 3 feet down. So 3 feet. So that's 16 plus 8 y by dt is 0. 8 dy by dt is negative 6. I'm sorry, it's not 8, 6. 2 times 3 is 6. So dy by dt is negative 16 over 6, which is negative 8 over 3 feet per second. So at which rate is the top of the ladder moving down? It's moving down at a rate of 8/3 feet per second, and down because it's negative, okay? Now I want to do few more examples. The next one that I want to do is number 4 from your handout. There's a handout. It's typed handout in the notes. If you look through notes for that section, it says related rates problems. I'm going to do number 4 from that right there, okay? A boy 4.5 feet tall walks toward 10 feet above the ground at the rate of 6 feet per second. By the way, this handout is also posted on D2L, and the solution is also posted on D2L under related rates handout, and then the solution. So it's all in on D2L, and it's included in the notes as well. So a boy 4.5 feet tall walks toward a light 10 feet above the ground at the rate of 6 feet per second. How fast is his shadow changing in length? And there's the answer. But again, the solution is also on D2L, not just the answer. Okay, so let's see. A boy is 4.5 feet tall. So assuming this is the boy, 4.5, that's constant, that's not changing, is walking towards a light. So the boy is moving this way, 10 feet above the ground. Again, the light is fixed. It's 10 feet. And this is the ground. So there's a light here. At the rate of 6 feet per second, dx by dt, that if this is x, dx, so that's getting smaller, so it's going to be negative, even though tell us it's negative. As x is shrinking, its rate is negative. How fast is his shadow changing in length? So if this is the boy, the shadow would be right here. Let's label it y. So we want dy by dt. Okay. And in order to do that, we have what we call similar triangles. These two sides are equal, they're parallel. That means these angles are equal, meaning the smaller triangle and the bigger triangle. I'm just going to label them so you know talking about ABC and ADE are similar. ABC and triangle ADE are similar triangles, meaning their sides are in proportion. Their sides are in proportion. So if we start with the bigger triangle, this side, which is x plus y relative to 10, x plus y relative to 10 equals so we use the bigger triangle versus the bigger triangle, and then the smaller, so y to 4.5. And this is not the only ratio, but we can do many of them. So if we cross multiply, 4.5x plus 4.5y equals 10y, 4.5x, 10 minus 4.5 is 5.5y, divide by, so y equals 4.5 over 5.5x. If we differentiate with respect to t, we get dy by d equals 45 over 55, because we can times by 10. So divide by 5 is 9, divide by 5 is 11, dx by dt. So 9 over 11 times negative 6, which is negative 54 over 11 feet per second. So you can see that that shadow is shrinking at a rate of 54 over 11 feet per second, which is about 4.9 feet per second. Okay, now we're going to go to the textbook. I'm trying to do a variety of problems. Number 4, page 251 in the textbook. It says the radius of a sphere is increasing. The radius of a sphere is increasing at a rate of 4 millimeters per second. dr by increasing, meaning it's positive, millimeters per second. How fast is the volume increasing when the diameter? So we want dV by dt when? At the instant when the diameter is 80 millimeters, meaning the radius is half the diameter, which is 40 millimeters, okay? Right, and then now we gotta know the volume of a sphere formula, 4 over E pi r cubed. So we got the formula. We don't need to draw a sphere. There's no need for that. We're gonna differentiate always with respect to time when we do related rates. So dV by dt, all this is a constant. And derivative of r cubed is 3r squared. And don't forget dr by dt, because the independent variable is t. We're doing implicit differentiation. So we want dV by dt for pi, right, when r is 40, so 40 squared, and dr by dt is 4. So if we do the math, we get 25,600 pi cubic millimeter per second. And you can put a decimal for that. I just left it as is. Okay, page 251 again, or 16. Page 251, number 16. At noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? So at noon, so at 12 p.m., ship A is 150 kilometers west of ship B. So this is ship B, west of it, that's west, that's east. So that's 150 kilometers at noon, okay? Ship A is sailing east. Ship A is going this way at 35 kilometers per hour. So if this is x, then dx by dt is negative, and you can see why it's negative rate, because that distance is shrinking. And ship B is sailing north. Ship B is sailing north at 25, so that's increasing. D by dt is 25 kilometers per hour. How fast is the distance between the ships? Let's call this z. We want to know dz by dt at 4 p.m. meaning 4 hours later. 4 p.m. meaning 4 hours later, because they started at noon. Okay, so obviously the Pythagorean theorem, x squared plus y squared equals z squared. None of these is a constant, they're all changing. So if we differentiate with respect to t, 2x d by dt plus 2y dy by dt is 2z dz by dt. I can divide everything by 2. So I would get x dx by dt plus y dy by dt equals z dz by dt. Let's see what we're given. Okay, so x is not going to be 150 because that was at 12. We want to know what happens 4 hours later. Okay, that's moving at a rate of 35 kilometers per hour in 4 hours. So the rate of x is 35 kilometers per hour. So that ship A would have traveled in 4 hours. It would have traveled 4 times 35, 140 kilometers, meaning x at this point x is only 10 kilometers, because it would have traveled 140, so that distance would have shrunk to only 10 kilometers, right? Started 150 apart, traveled 140, so x is only 10. So 4 hours later x was 10. dx by dt is negative 35. When x is 10, we don't know y and we don't know z, but we can find y, because dy by dt is 25 kilometers per hour. In 4 hours, y is going to be what? 4 times 25, which is 100 kilometers away. That ship will be 100 kilometers away from point B. So y is 100. Here, I'll do it here. So 10 times negative 35 plus 100, and dy by dt is 25. And now we can find z when x is 10 and y is 100. What is z? So z squared is 10 squared plus 100 squared. And so z is square root of 10,100 dz by dt. So if you do the math, dz by dt is going to be 21.4 kilometers. So that distance between the two ships is increasing at a rate of about 21 kilometers per hour. Okay, next one. Here, it's not from the book or from the handout, it's in my notes. It says, I'm gonna write it down, although it's written in my notes. Water is flowing into a conical tank vertex down at the rate of 10 cubic feet per minute. At what rate is the water level rising? Is the water level rising at the instant when water is 8 feet deep? Sorry, I'm writing fast, but it's all in the notes. So we have a cone, vertex down, and water is flowing into the cone at the rate of 10 cubic, so it's increasing, right? It's getting filled up. It's a volume over time, right? Cubic feet is the volume, minutes, so dV by dt. At what rate is the water level rising? So we want to know, there are two changes here, the water level and the radius of the circular top. At what rate is the water level rising? At the instant when water is 8 feet deep. So we want dH by dt when h is 8. And we're given a couple more things. We're given that this is 10 feet across, and we're given that this is 12 feet high. So we know the water level changing, so we have a similar triangles right there, smaller and the bigger triangle. The smaller, so if this is R, these are changing, and these are fixed. This is 5 and this is 12. 10 across, that meaning 5 is the radius. So the ratio of R to H is 5 to 12, right? R to H is 5 to 12 using triangles. So R is 5 over 12H, so dr by dt is 5 over 12 dH by dt. So that's the relationship between the rates of R, because we're given this, we can find that. Okay, but we don't need that now. So the volume, the formula is 1/3 pi r square h. We want to find dH by dt, so we want to get rid of r, so we use 5 over 12h in there for r. So b is pi over 5h over 12 square times h. So v is 25 pi over 432 h cubed. If we do the math, so dv, so let's do d by dt, dv by dt, all this is a constant. Derivative of h cubed is 3h squared dh by dt. So dv by dt is 10. That equals 25 pi over, if you reduce this root there, that's 144. H is 8. And dH by dt is the unknown. So you do the math. dH by dt is 9 over 10 pi feet per minute. Okay. Now, if you look at my notes, I want you at this point to do number 1 from the handout, and the workout is there. So I'll let you do that on your own. Number 1 from the handout. And it's also solved on page 54 for you, but try to do it without looking. What?